Hello. Today we are going to dive into the engine room of modern healthcare analytics, feature engineering for clinical time series. Healthcare is a gold mine of information, but the data is raw and chaotic. Electronic health records, EHRs, collect data in multiple streams. We have high frequency data, like heart rate from an ICU monitor, episodic data, like lab results that only happen every few days, and discrete events, like a physician's note or a specific medication given for acute reasons. The fundamental problem is that raw data is messy and unstructured, especially clinical data. Standard machine learning models cannot ingest raw streams directly. Our goal is to understand the core techniques that transform this noise into structured, predictive features that are foundational inputs to allow us to build reliable clinical AI. If you have worked with financial or IT data, you might be used to relatively clean, uniformly sampled time series data. Clinical data is the opposite. Clinical data is defined by irregularity. Let's think about a typical patient. Tests are not administered based on a clock, they are administered based on clinical need. A stable patient has vital signs taken occasionally, while a crashing patient has them taken continuously. This leads to two critical problems: variable intervals between readings and large blocks of missing data. If a lab test is not ordered, it isn't just a blank spot in the data, it means the clinician deemed the patient stable enough not to need it. And we must account for this in the clinical context. Our first step in creating structure is windowing. We cannot analyze a patient's entire history. We have to segment the timeline into defined observation periods. The most common method is the sliding window or look-back window. For example, if we are predicting a risk event right now, we might extract features based strictly on the data collected in the preceding 6 or 12 hours. Another method is the event-anchored window. This is vital for retrospective studies. If we're studying outcomes from an ICU admission, we don't look at all of the data at once. We create a rigid window strictly focused on the 24 hours prior to admission to capture the data that is driving that particular transition. Windowing transforms chaotic history into structured data. Once we have defined our window, we must summarize the data within it. We have raw data points, but we need single values, the features. This is aggregation, a key data reduction technique. Traditional statistical aggregators like mean or median are useful baselines, but they can mask critical signals used for clinical practice. In medicine, the extremes often tell the best story. When aggregating vitals, the maximum and minimum values are usually more predictive of risk than the average. A patient's temperature averaging 99 degrees is less important than a momentary spike to 103 degrees. We must consider metrics of recency, often using last observed carried forward, or LOCF, to represent the patient's current known state. We have structured summaries now, but we are missing an important aspect of clinical assessment: change. How is the patient trending? Our next class of features are called dynamics. The first dynamic is trends or trajectory. We want to quantify the direction and rate of change. By fitting a simple linear regression, we can extract the slope of the line. This gives us a concise mathematical feature quantifying whether the patient is improving or deteriorating. Our second dynamic is variability or instability. A physiological signal can be within a normal range, but still show fluctuations. This is high signal-to-noise ratio behavior. We quantify this using dispersion metrics like standard deviation and coefficient of variation. For example, a high respiratory rate variability is a precursor to systemic failure in conditions like sepsis. By synthesizing these core techniques, windowing, aggregation, historical trends, and quantifying variability, We successfully pipeline irregular clinical data into a clean, structured feature matrix. This is the foundational step. Whether you're building an early warning system for sepsis or forecasting lengths of stay, your model is only as robust as the features you provide. Good feature engineering does not just manage data, it respects the clinical context, transforming noisy data into actionable signals. Thank you very much. For more information, you can reference this Notebook LM notebook at the